In this video, we're going to introduce the concept of a vector. In particular, we're going to look at some terminology and some notation that correspond with it. And it turns out that in order to do calculus with multivariable functions, the underlying machinery to do derivatives, integrals, and all these other things relies upon vectors in vector algebra. So we really have to take our time with vectors and really understand how vectors work and how different operations that we can use on vectors to create new vectors and so forth. And so really, again, this isn't going to look like calculus, but it will eventually lead into doing calculus on multivariable functions. So the first thing that we need to really understand is what is a vector. And we're going to start to answer that question by looking at what a vector is not. And so there are certain quantities that are called scalars. So these are quantities that involve a number only. So quantities involving, another way of saying that only involves numbers, maybe I'll say quantities involving magnitude only. So for example, things like length, things like temperature, speed. These quantities only involve a number. So a length is, once we pick a unit, like say feet, it's 7 feet. Something is 7 feet long. It doesn't tell us what direction the object is pointing in or what direction the 7 feet is going. Same thing with speed. If I know an object is moving 50 miles per hour, I have no idea what direction the object's moving. It could be moving horizontally down a road. It could be moving straight up in the air. It could be moving straight down. Right? We don't know anything based on those quantities. So these are going to be called scalars when we just have a numerical value. Right? On the other hand, we have some quantities need more than that. And these are what we're going to refer to as vectors. So a vector, for our purposes, will be a quantity that represents both a magnitude and a direction. Right. So some common examples of this would be velocity. Right? When you've seen velocity in past calculus classes, you had positive velocity and negative velocity. So that positive or negative sign indicated whether the object was moving in the forward direction or in the reverse direction. As it would probably, as it makes sense at this point, since we're now in three-dimensional space, there are more possible directions to move than forward or backwards. We can move up, down, left, right, all sorts of different areas. So we have different directions. So we have to be able to define it more generally than just a positive or a negative sign. Right? And we can also have things like forces. All right? So this is kind of getting into the more physics side of things. But for example, gravity. Gravity is a force that has a magnitude. There's a strength of gravity that's related to how close to the object you are. And there's also the direction of the pull. It's pulling you towards that object, right? So those are a couple of quantities that are represented with vectors. We're going to be primarily concerned with vectors either in the plane or in three-dimensional space, and so we can represent vectors in those domains as arrows. So for example, in the plane I'm going to denote throughout the course by R2. The R's, the blackboard R stands for the real numbers. The 2 is that we have 2 dimensions. So we have 2 real lines, the x-axis and the y-axis, that are making up the entire region. And so if I have my xy plane here, I can draw an arrow in the plane. Maybe it starts at this point and it goes up there. And I can call this U, and I might put a little arrowhead on the top of it. And that's going to be our notation to indicate that we're talking about a vector. And so a vector is a magnitude, it's a number, and a direction. Well, the magnitude is going to be the length of this arrow in the plane. So I have the tail, that point that I started with, the initial point. So this point here that I started, this is going to be called the initial point of u. Right, it's the point where the vector begins. And the point where the vector ends, didn't really draw it, but it's the tip of the arrow there. This is going to be called the terminal point. So the magnitude that represents a vector is just going to be the distance from the initial point to the terminal points, the length of the arrow. The direction of the vector is going to be quite literally the direction the arrow points. Right? And so that arrow is able to show us both quantities simultaneously. And now, of course, there's other arrows I can draw. I could draw one like this. Maybe I'll call this vector v. Again, we'll put the little arrow on top to represent that it's a vector. And I could draw a third vector here, but instead of just drawing the arrow and then labeling it, let's say we wanted to draw a vector that started at a point P and ended at a point Q. Right, so I have these 2 points P and Q, and I want the vector that goes from P to Q. So I'm explicitly identifying the initial and terminal points here. Right, if I want to write this, I could of course call this something like W with the arrow over it, but I can also use the 2 points P and Q to be very clear about what this vector is. So if this were the case, what I might do is I would write PQ with the arrow over both letters, but pointing from P to Q. So notice that this is telling me that the initial point is P and the terminal point is Q. If I write QP, then that means I have the arrow, the vector that starts at Q and goes to P. So it would be actually in the opposite direction. So we want to pay attention to the order that the vectors are listed, or the points are listed in the notation for the vector. Right. Now, everything we just did was in the plane, but it extends in the obvious way to R3, or 3 space. Okay. So if I have my X, Y, and Z axes here, so this is X, this is Y, and this is Z. If I have a point P, maybe a point down here, this is P, and another point up here, which we can call Q, then I can just connect these points in 3 space with an arrow, and this will be the vector PQ. Right? Vector from P to Q. Right? Now, of course, again, just like with everything else in 3 space, this is hard to see in 2 dimensions, but you can imagine what's happening here. There's 2 points in space, an arrow going from one to another. Right? With this in mind, it doesn't really matter if we're in the plane or in 3 space for these next couple things, but we want to talk about a few different properties that vectors have. The first thing is that vectors are defined in terms of magnitude and direction. We didn't say anything about the starting point when we defined a vector, and that's because we really don't care. In general, in an application, we probably would, but if we're talking algebraically, we really are just looking for size and magnitude and direction. So going back to this R2 example, I have vectors u and v. If you look at them, you'll notice that they look approximately the same length, all right? And that was intentional. So let's say that they are, let's just say that they are exactly the same length, or that they're intended to be exactly the same length. They also look to be in the same direction. Again, that was intentional. So in this R2 picture, we would actually say that the vector u is equal to the vector v. And the reason is that they have the same magnitude and the same direction. Okay. So this is somewhat unusual for mathematics, that we have 2 things that are clearly different. They're different arrows in the plane, but we're actually going to say they are equal. But in this case, the vector is only recording the length, the magnitude, and the direction, not necessarily the starting point. So we would say these are actually equal. Right? We also have vector v. We're going to say that that is in standard position. Right? So standard position simply means that the initial point is at the origin. And by having a vector in standard position, it allows us to be able to write down that vector in a very nice way. Right, so to see what I mean by that, let's say we have a vector v, like the one that we just had in the previous picture. Let's say it was in standard position. Right, so we know its initial point is at the origin. Well, if that's the case, then what we know about that is that we know v has a unique terminal point. Right, and that terminal point, if we're in R2, is going to be maybe the coordinates v1 or v2. So if we're in two-dimensional space, we have an x and a y coordinate. Or if we're in three-dimensional space, that terminal point can be described by an ordered triple, v1, v2, or v3. Right, and this fact that there's a unique terminal point is fairly intuitive. It's the idea that if you look in a certain direction, whichever direction that happens to be, there's exactly one point that is a fixed distance in that direction. So if you're standing or sitting wherever you are right now and you look in some specified direction and say what point is exactly 17 inches in front of you, there is a unique point right there. Right? And it doesn't matter if someone else comes and sits in the exact spot that you are, looks in the exact same direction, and goes out that same distance, they will have that exact same spot. And so we can actually use this terminal point to describe the vector. Right? So this leads us to the following definition. So if we're given a vector v, that's in standard position, and it has a terminal point of v1, v2, or v1, v2, v3, depending on whether we're in the plane or in 3 space. We're going to define the component form of v to be either v1, v2 in angle brackets, or v1, v2, v3 in angle brackets. So the way that the component form of a vector will work is that we put the vector in standard position, we find the terminal point, and we use the coordinates either in R2 or R3 of that terminal point as the notation for the vector, except we use angle brackets instead of parentheses to denote that. So this way it's clear if we're talking about the point v1, v2 or the vector v1, v2, which is the directed arrow from the origin to the point v1, v2. Right? Once we have the component form, these numbers v1, v2, and v3 are called the components of v. So v1 would be the first component, v2 the second component, and v3 the third component. So for a quick example, let's say we have the following vector in R2. We'll make it in standard position. Okay. So the terminal point of this vector will be the point 3, 2. Right, so if this vector, if we called this v, then the component form of v is simply 3, 2. Right? On the other hand, let's say we had a vector, and we call it w. We'll give one in component form. Maybe we'll call it -1, 1. So we have this vector here. Right? So if I want to draw this as an arrow, this tells me that I want to start the vector at the origin and I want to go to the point -1, 1. Right? -1, 1 will be right here. So there would be -1. And so the vector w is this vector right here, right, in blue. Right? And so the graphical way of thinking of vectors in terms of arrows, directed arrows in the plane or in 3 space, is a very nice geometric way of thinking of it, a very intuitive way of thinking about it. But it's really hard to do calculus with arrows in the plane. So this component form will allow us to write vectors numerically in a more functional way, so that we can use them with functions and be able to perform calculus very easily. So one last thing we want to talk about with just the very basics of vectors is the idea of the length of a vector. We want to give that a name. And unfortunately, it doesn't have a single name. There's actually several words that are used in different contexts to describe the same thing. So we're going to define the length / the magnitude / the norm of a vector. Right? So all 3 of these words are used interchangeably. And unfortunately, this is just one of the unfortunate things of vector theory, is that a lot of words are used to describe the same concept. In this case, these are the 3 most common ones. So length, magnitude, and norm of a vector v in component form, which is either going to be v1, v2, or if we're in 3 dimensions, v1, v2, v3. So the length, magnitude, or norm of this vector, which is going to be denoted by the vector v in absolute value bars, is given by the following formula. Okay? So the magnitude of v is going to be the square root of v1 squared plus v2 squared, or if we're in 3 dimensions, the square root of v1 squared plus v2 squared plus v3 squared. Okay. So we're defining the length, magnitude, and the norm, whatever you want to call it, for both 2-dimensional vectors and 3-dimensional vectors simultaneously. So this kind of looks familiar. We've actually already used the vertical bars notation in 3 dimensions, and we use that to describe the distance between 2 points. But if you notice that this is just the distance from the point v1, v2, or v1, v2, v3, and the origin being 0, 0, or 0, 0, 0. So really, this is nothing new. This is just the distance formula that we discussed in one of the previous videos in disguise. Right, so this is already something that we knew. Right? So let's look at the following example. Let's say I have 2 points. So I want to let P be the point, -1, 3, -2. And I want to let Q be the point 0, 1, -5. Right, so I have 2 points in 3 space here. So what I'd like to do is I'd like to find the vector PQ and then the length, the magnitude, the norm of vector PQ. So I'd like to find both of these two things. Right? So to find vector PQ, right, so we have to remember this is the vector from P to Q. And so if I want to focus on the first coordinate of this vector, this is going to be the difference between the x coordinates of the initial and the terminal points. And so we would always take, it's going to be the first coordinate of the terminal point minus the first coordinate of the initial point. So the first coordinate of the terminal point is 0. The first coordinate of the initial point is -1. So the first coordinate of my vector P to Q is going to be 0 minus -1. Right? Similarly, for the second coordinate, we're going to take the second coordinate of the terminal point, which is 1, and subtract the second coordinate of the initial point, which is 3. Right? And then for the third coordinate, we have the third coordinate of the terminal point minus the third coordinate of the initial point, so -5 minus -2. Right? And now we just perform the one-digit arithmetic. So we have 1, -2, and -3. So PQ is the vector 1, -2, -3. That's the component form for vector PQ. Right? So if we were representing this as an arrow in the plane, we would start the arrow at the origin, and the arrow would end at the point 1, -2, -3. Right? Now once we know the component form, the magnitude or the norm or the length of the vector is quite easy to do. It's the square root of the sum of the components squared. So it's the square root of 1 squared plus -2 squared plus -3 squared. So this would be the square root of 1 plus 4 plus 9. And that is the square root of 14. Right, so this vector that goes from the origin to the point 1, -2, -3 is square root of 14 units long. Right, so in our next video, we're going to start talking about vector algebra. So if we have multiple vectors, how can we add, subtract them together to form new vectors, and how can we multiply vectors by scalars to obtain other vectors? This turns out to be the basis for everything that we will end up doing with vector functions, and so that will be introduced in our next video.